Welcome back to our series of lectures on the topic physical properties and molecular structure. In this series, we have been trying to establish the correlations between the physical properties and the structure of matter. In this concluding part, we will take up two issues today. The first one happens to be the measurement of dipole moment, and the second one is about the magnetic properties of matter. We will talk about the magnetic properties at atomic level and the bulk magnetic properties. The session is planned as follows. That is, to begin with, we will briefly review the contents of previous sessions, and then thereafter we will talk about the measurement of dipole moment. And having done that, we will move on to the origin of magnetic properties of matter at atomic level. And thereafter, we will move on to the bulk magnetic properties, that is, what kind of magnetic properties do we observe for bulk matter. And in this context, we will talk about different kinds of magnetic behavior, paramagnetism, diamagnetism and things like that. And towards the end, we will try to sum up what we do in today's session. Let us begin by recalling what we have done so far. You remember that we started by defining what is optical activity and explained the concept of optical rotation, whereby the plane of plane polarized light is rotated by an optically active material. Having done that, we explained the origin of optical activity. That is, we went deeper into the concept and we saw that how do we rationalize the optical activity of materials. Then we also tried to correlate that with the structural requirements for the same. Thereafter, we moved on to the concept of electric dipole and kind of quantification of the same in terms of dipole moment. And then we kind of correlated the dipole moment and the structure of polyatomic molecules. Thereafter, we moved on to another domain of physical properties wherein we talked about the polarization of dielectric, and in this context we recalled the basic concept of capacitance, and thereafter we explained what is this phenomenon of polarization of dielectric, well, what kind of things happen at the molecular level, that is, we rationalize that in terms of the things happening at molecular level. Then thereafter we kind of worked out the expressions for orientation, distortion and molar polarization of a dielectric medium. Now, this is all what we have done so far. Let us move further and see that how do we kind of measure dipole moment. That is the first thing we want to take up for today. And for this, we will like to recall what we did in the previous session, that is, we recall what is called as Debye equation. Remember that this is the Debye equation wherein this Pm happens to be molar polarization, and that is the bulk property of the matter, and Er is the relative permittivity or dielectric constant, m is the molar mass of the material, and rho happens to be the density, Na is the Avogadro's constant, epsilon naught is the permittivity of the vacuum, and then alpha of course is the polarizability, and mu happens to be the dipole moment of the material there, and K is Boltzmann constant, T happens to be temperature. So, we are familiar with this term. Now, if I just want to make things easier for ourselves, we just try to rewrite this equation. We write Pm, that is molar polarization, to be equal to, we just open these brackets and write the following expression there. That is, we find that the molar polarization happens to be dependent on two properties there. This is a bulk property and these two are the molecular properties, alpha, that is the polarizability, mu, that is the dipole moment there. And if you see it closely, that this expression can be expressed in terms of a equation of a straight line, that is Pm to be equal to A plus B by T, because if I just see here, all of these are constants for a given material, and in this case everything else other than the T happens to be constant there. So, we can express it as a equation of a straight line, and this is what we are going to make use of. Now, what you find is that if this is a straight line equation and if I try to plot Pm, that is a molar polarization for the material at different temperatures, that is, I make measurements at different temperatures for the molar polarization and try to plot a graph between the molar polarization on the y axis and 1 by T on the x axis, I will get a straight line there. And in this straight line, the slope of the straight line will be giving me V, which actually is equal to Na mu square by 9 epsilon naught K. So, we know all these things here. So, knowing B from the slope of the line here, I can get the value of mu here. That is, the dipole moment can be obtained from the slope of the line. So, that means the experimental setup is very, very straightforward. What do? We determine the Pm at different temperatures and make a plot between the Pm and 1 by T and get the slope of the line. And the slope of the line gives me the value of mu from this expression over here. But the question comes is, how do I get Pm? Temperature is straightforward. to how to get Pm, let's look at this expression. You see that Pm to be equal to Er minus 1 into m, that is a molar mass there, Er plus 2, rho, that is a density here. So, what we do is, to begin with, we use common kind of typical methods to determine the molar mass and the density of the material. This is very straightforward. There are a number of methods to do that. And what is important here is, in order to get the value of Pm, we need to know Er. And we learnt in the previous session that Er, the relative permittivity or the dielectric constant, actually is nothing but the ratio of the capacitance of a capacitor in the presence and absence of the dielectric medium there. So, we make use of that. That is, we make the measurement of relative permittivity, that is the dielectric constant of the material, by measuring the capacitance of capacitor with and without the dielectric medium there, or the dielectric here basically is the material for which we want to find out the dipole moment there. So, we know Er, we have already determined m and rho. So, we substitute over here and get the value of Pm. Once we get the value of Pm, that we can do at different temperatures there, and then everything else follows thereafter. That is, we have Pm values at different temperatures, make a plot, get the slope, and from the slope get the value of dipole moment. So, it is a very straightforward kind of a determination. The principle is very straightforward. The only thing is the measurements are a little involved here. So, this is very straightforward, a simple method of determination of dipole moments there. Let us move further and talk about the magnetic properties now. That is the main theme for today, because this was one bit which was to be continued from the previous sessions. Now, as regards the magnetic properties, let us talking about the magnetic properties, the origin of them at the atomic level, because the magnetic properties are different kind of materials we come across. The origin of that lies at the atomic level. Let us see that. We know that in an atom, the electrons move around the nucleus in orbitals. If we look at a simplistic model, the Bohr's model, we can represent something like this. We have a nucleus here and the electron is moving around in a orbit there. We know that it is a simplified version. We know that the electron moves in a orbital there. But what is important is that since electron is a charged particle and it is moving in a particular circular path in this case as shown over here. So, it generates some kind of a current loops there, because this moving charge is going to create current loops, which in turn will produce some kind of magnetic field there. So, that is called as the kind of orbital magnetic moment will be generated by that. In addition to that, we also know that the electron spins on its own axis. So, because of the electronic spin, there is an additional component of magnetic moment which will come there. So, the total magnetization at atomic level is the sum total of the two components. One is the orbital component and second happens to be the electron spin component there. So, the two put together give the overall magnetic moment for a given atomic system over there. But when we move further, we find that if the direction of the magnetic moment, that is the overall magnetic moment for a given atom, depends on the sense or the direction of the orbital motion and the electron spin. In case the directions are reversed, so the effects also will be changed accordingly. What is important here is that in case it so happens that the atoms or the ions we are talking about, which is constituting the matter, if they contain all paired electrons, that means electrons are all paired up, then in that case the magnetic moments of the electrons will nullify each other. That means the magnetic moment of an electron which is aligned, say it is having a positive spin, or the one which is having opposite spin, the two will cancel each other and there will be no net magnetization in the system there. Now, let us move further and talk about the bulk properties there. What you find is that is the bulk magnetic and electrical properties of molecules and solids are analogous. What it means is that is we have learnt about the electrical properties of the materials in the previous session, where we talked about the electrical dipole and things thereafter. Similar to that, in case of magnetic systems also, the bulk magnetic properties also run parallel to that. What it means is that is in case of electrical properties, we saw that there is a polarization P coming into picture. That means we have a material and when you put the material into an electrical field, some kind of a polarization comes into play. That is a consequence of putting the material into an electrical field. Similar to that, if I put my material into a magnetic field, there will be something called as a magnetization, and that is given by symbol M over there. So, the two run parallel to each other. Further, the magnetization of a sample of a matter by a magnetic field is similar to polarization of a dielectric by an electric field. So, that is a re-emphasis of the same statement over there. Now, let us see that if I have a sample wherein which has got permanent magnetic dipole moments, that is the constituents of the sample have got permanent dipole moments, but the net magnetic moment of the material or the sample will be 0. because of the randomization by the thermal motion, because all the components, the atoms, molecules, etc., in a given system are constantly under motion there because of the thermal reasons there, and because of that all these magnetic moments get randomized, and the sum total of all that put together happens to be 0. That is, there is no net magnetization. But the moment I put such a material into a magnetic field, what happens is that these magnetic dipoles, which were randomly oriented earlier, now they start aligning with the field, and in the process the field in the medium, the magnetic field in the medium increases, and the sample is said to be magnetized. That means we do like we remember that in case of electrical field application there was kind of polarization. Here we got magnetization there, and magnetic field, you know, typically can be generated by using a solenoid. Let us understand that. Now, if I have a solenoid which contains magnetic material, so in that case what happens is the magnetic field, due to the magnetic moments induced by the field, also add to the field, because earlier what we do is we have got a solenoid here, we have kind of passed current around the loops over there, and there is some kind of a magnetization over there which has been generated by passing current through these wires which are coiled around the solenoid there. So, there is some kind of a field B naught over there. But if the solenoid is not empty here, it contains some magnetic material shown in a color over here, that is, into this cylinder there is some kind of magnetic material embedded in that. So, in such a case what happens is there is some kind of a magnetization is induced into this material, and the total field what will be observed will be sum of the field which is obtained because of the solenoid here, that is this B naught here, and plus there is a small component which is called as a magnetization will come into picture, that is mu naught m over there. B naught is the initial field, that means you apply certain amount of current, we get a field B naught. But if this solenoid contains a magnetic material, the field happens to be B, which is larger than the B naught. That is, we can write B to be equal to B naught plus mu naught m. This is the component which has come from the magnetization. This is the magnetic field otherwise over there. Now, as I just mentioned, B naught is an applied magnetic field, mu naught is the permeability of the vacuum, and m happens to be magnetization there. Now, what happens is if the applied field, that is the field which was generated because of the passing current around the solenoid, if it is not large, we find that the magnetization what is there m is proportional to the applied field, and in such a case we can write B to be equal to mu r B naught, where mu r happens to be relative permeability, and B naught of course is the applied field over there. Now, in such a case, if I just substitute it into the previous expression and simplify, I find that mu naught m, that is the magnetization which I generated over there, is equal to 1 plus mu r into B naught, and then this term 1 plus mu r is called as chi mag, or it is called as a magnetic susceptibility. It is a very important parameter to characterize the bulk magnetic properties of the materials there, and this actually is by using the determination of chi mag we can work out that what is the susceptibility, and that gives an indication about what kind of material are we dealing with. And the measurement of magnetic susceptibility is very simple. We use what is called as Gauss balance for that purpose. It is a very simple device. What do we do is, actually this device is based on the interaction between the unpaired electrons and the magnetic field. In this case what basically happens is there is a magnet here, there is a kind of electromagnet, and this is a sample tube wherein we put our material for which the susceptibility has to be determined there, and this is tied to some kind of a weighing scale over there through a fulcrum here. Now, what do? We put the sample into this in such a way that most of it is, well, the bulk is here, and then some sample is up over here also, and there is no field to begin with. That means this magnet is not there, and in the absence of magnetic field we find out what is the weight of this material, that is the sample tubing and the material contained in that. We get the weight over there, and then we generate magnetic field over there. When you generate magnetic field, two things can happen, that is this magnetic material which is contained into this sample tube is either repelled by the field or it is attracted by the field. That is, if the material happens to be diamagnetic, we will talk about this in little details little later. That is, if material is diamagnetic, we find that this magnetic field repels it. If it repels it, the weight changes, it becomes lesser. And on the other hand, if a material happens to be paramagnetic in nature, so this will be pulled into by the field. As a consequence, the weight measurement here which is displayed on the scale will be higher there. That is, this kind of interaction of the magnetic field and the material is manifested in terms of the change in weight of the material there, and that is read over the scale over here. Now, this kind of a device is called as Gauss balance. Now, let us move further and see that how do we talk about the bulk magnetic properties. We find that depending on the nature of magnetic moments at atomic level, that means different materials have got different magnetic moments at atomic level and their behavior in the absence and presence of magnetic field. So, the bulk matter shows different magnetic properties. What it means is that if I look at a bulk matter, and the magnetic behavior of that bulk matter will depend on what are the constituents of that, what is their magnetic moments over there, and how do that magnetic moments behave in the presence and absence of the magnetic field. So, all put together determines the nature of the magnetic material there, and on that basis the bulk magnetic properties can be classified into, say, diamagnetism, paramagnetism, ferromagnetism, antiferromagnetism and ferrimagnetism. We will talk about each one of them one by one. We start with diamagnetism. Diamagnetism is very straightforward. In most substances, what we find is that the magnetic effects of electron spin and electron orbit motions cancel as the electrons are paired up, because since the electrons are paired up, as I showed earlier also, whenever electrons are fully paired up, the material happens to be diamagnetic. That means there is no net magnetic moment at the atomic level there. Accordingly, there is no net magnetization. That is, if I take the material in the absence of an external field, there is no net magnetization. But the moment I put that material into a magnetic field, then what happens? Then what happens is that the orbital motion of the electrons gets modified, and that gives rise to minute amount of magnetic moments, and those magnetic moments are such which oppose the applied field. And if I remove the field, we find that this kind of a magnetization which is generated is lost. Let us look at next slide here. So, if I have got this represents my material I am talking about, we find that all these constituents of the material they are non-magnetic. There is no magnetic moment in any of them. Now, what do I do is I apply a field on that. The moment I apply a field, I find that some kind of small tiny magnets are generated onto these materials. That means the constituent, that is the atoms or the constituents of the material there. So, this is, and we find that the small magnetic moments which are generated, they happen to be aligned opposite to the applied field, and this behavior is typical of diamagnetic material. And if I remove the field, we find that even that magnetization which was generated is lost. That means this effect of kind of a tiny magnets coming into play is operative only in the presence of applied magnetic field. In the absence of field, there is no net magnetization. That is typical of diamagnetic materials. Most of the materials are diamagnetic because the diamagnetism is present in most of the materials there. Let us look at some more features of diamagnetism. Now, this picture on the left shows here, that is, if I have this circle is representing some sample of the material I am dealing with. Now, if this B naught happens to be a magnetic field, if I put some kind of a sample compartment here which contains nothing, suppose there is a vacuum in this, we find that the field, these are the lines of force of the field, they will pass smoothly through that. But in case it so happens that is the sample compartment contains a material which happens to be diamagnetic, then what happens is the number of lines of force which pass through it are slightly less than that will pass through the vacuum. That means, in case of vacuum, all the lines of force are passing through this. But if it happens to be diamagnetic material, we find that some lines of force are going out of it. And as a consequence of this, such materials experience repulsion in the magnetic field. That is what I told in the context of Gauss balance. If it is a diamagnetic material, it will be thrown out of the field there, and the weight will be observed to be lesser there. And for such materials, we find that chi, that is the magnetic susceptibility, is very small and slightly negative number there. That is typical characterization of diamagnetic materials there. Now, let us move on to the second kind of bulk magnetic property that is called as paramagnetism. It is very interesting and useful property here. In certain materials, what you find is the constituents have got permanent magnetic depots to begin with. That is, this is possible because we know that typically oxygen is paramagnetic, because in oxygen molecule there are unpaired spins there, and because of the unpaired spins, whether we are talking about the oxygen molecule or we talk about certain transition metal elements and compounds, we find that they are magnetic to begin with. So, in this case we find that because of the unpaired spins or due to angular momentum of electrons in orbitals, etc., there is some kind of a magnetic dipole moments to begin with in the material. Now, if I just take a sample of such material, we find that these magnetic dipoles are randomly oriented, which is typically expected. That means there is no reason for these dipoles to be oriented in a given direction. So, they are randomly oriented there because of the thermal motion, and that means there is no net macroscopic magnetization. At microscopic level, that is at atomic level, there are tiny magnets over there, but the magnets are randomly oriented. So, if I put a sum total of all those randomly oriented magnetic moments, that comes out to be 0. That means for paramagnetic materials, there is no net macroscopic magnetization in the absence of field. But if I apply field, then what happens? Then what happens is that these dipoles, they start aligning with the field. As a consequence, we find that things change here. Let us look at it. Now, this is a typical representation of a paramagnetic material. What I am showing here is these are the constituent, say, atoms or the particles of the material there, and the arrows here are indicating the permanent magnetic moments of the constituent species over there, and we see that these all are randomly oriented. So, that is the bulk matter to begin with in the absence of the field. Now, if I apply field, what I find is that these randomized magnetic moments, they get altered and they align with the field. So, this is typical paramagnetic behavior, and when I remove this, I find that this kind of alignment is lost and I get back to my original bulk material wherein the magnetic moments are randomly oriented. So, that is typical paramagnetic behavior. Now, let us try to look at a different perspective of the same thing. What you find is, if I am dealing with a paramagnetic material, so this is the same picture as I showed you earlier, that is, this is some chamber where it contains nothing, that is, it is having vacuum here. So, lines of force are passing through this. But if the sample compartment contains a paramagnetic material, we find that the lines of forces which are passing through this material happen to be more than that what they have passed through the vacuum there. That is just opposite of what we observed in case of diamagnetism or diamagnetic materials. In that case, there were fewer lines. In this case, there are more lines than what we expect in the vacuum there. So, a consequence of that is that such materials are attracted by the field, in the magnetic field there. And this picture shows a typical, a very common picture here, which shows that if I take liquid oxygen, and oxygen we all know fairly well is a paramagnetic material. If I take liquid oxygen and pour it through a strong magnet there, that is a magnet there, these two nuts here are indicative of the magnets over there. If I pour liquid oxygen through this, we find that it is held between these two. In place of this, if I had taken nitrogen, which is not paramagnetic, it will just flow down. Oxygen is held back over there because it is attracted by the field. So, that is a basic difference between diamagnetism and paramagnetism. And for paramagnetic materials, we find that chi, that is the susceptibility, is very small but positive. This again is opposite to what we had in case of diamagnetism. In case of diamagnetism, the number was small but it was negative. In this case, the chi value happens to be positive. That is why this chi is a very important parameter. So, just if I take a material, measure chi and find out what is the magnitude of that, that will give me an idea about what kind of material I am dealing with, whether diamagnetic or paramagnetic or something else. So, that is a very, very important parameter with us. Let us move further and let me make a statement here. Basically, the two effects, the two bulk magnetic properties I have discussed, that is the diamagnetism and paramagnetism, we find that these two effects are the ones which become operative only in the presence of external magnetic field. That means, on their own, these materials typically are called as non-magnetic, because though they show magnetic behavior in presence of applied magnetic field, but on their own they are non-magnetic. But there are many materials which are magnetic by themselves. Let us look at them. The third bulk magnetic property or the behavior is called as ferromagnetism. That is a typical, most commonly observed. Typically, when we talk about a magnet, we talk about ferromagnetism. What you find is that there are certain materials like iron, nickel, cobalt, etc. And these materials possess a permanent magnetic moment. And it is so that, so we look at the sample of an iron. So, we know that iron atoms have got permanent magnetic moment there, and in the bulk sample, where there are billions and trillions of the species over there, we find that these magnetic moments of individual atoms over there, they interact, that is the neighboring magnetic moments interact with one another, and that interaction leads to some kind of an alignment. That means, these magnetic moments within certain close by materials, they align with one another and they generate what is called as the domains there. So, what you see in this picture, that is this some kind of a boxes are made over there, small enclosures are there. So, these enclosures are called as domains. That is, what does it domain mean is that if I am looking at this particular domain, that is, and we see there is an arrow over here indicated like this. That means, and in this particular part of the material, all the neighboring atoms there, their magnetic moments are aligned in a given direction, such that sum total of that can be represented by the following arrow over there. That means, this arrow indicates the bulk magnetization of all the magnetic moments in this particular area of the material there. Similarly, we have another one there, yet another one, and so on and so forth. So, that means, the bulk matter is put into small compartments there, and in each compartment all the atoms magnetic moments are oriented in a given direction, and such that they all align in one direction. So, all magnetic moments will add and give rise to a net magnetization in a given direction. So, what you find is that in the bulk matter there are number of such domains there, and these domains, within the domain all magnetic moments are aligned in a given direction, but between the neighboring domains they may not be in the same direction over there. We can see that, say, in this domain magnetic moments are aligned in this direction, whereas here it is in this direction, and so on and so forth. So, what happens is that the sample as a whole can be split into different compartments or the domains, and within the domain all the magnetic moments are aligned in a given direction there. Okay. That is there even in the absence of external magnetic field, that is an intrinsic property of the material by itself. Okay. If that be so, that means there is some kind of a magnetization is there. Now, within the domain, as I mentioned earlier, most of the magnetic moments are parallel. However, the direction of alignment varies from one domain to another. That is very important. That is, in this domain the direction is this, in this domain the direction is this, and so on and so forth. That is very important characteristics of ferromagnetic materials there. Yet another characteristic of that is these domains, that is the magnetization, the bulk magnetization of each domain, these magnetizations are randomly oriented. That means, the vectors I am talking about, they are randomly oriented there. Now when I apply field, let us see what happens now. In the presence of field, the domains tend to reorient themselves parallel to the field, and in the process the domain boundaries also shift. This is the two effects are coming into play. Let us understand that. This is my bulk material in the absence of the field. We find that there are different domains and the net domain magnetizations are oriented randomly there. When I apply field, this is my applied field here. When I apply field, I find that in these domains there is some kind of a realignment comes into picture, and more kind of domains, they start aligning with the field, and as a consequence what happens is, that is, the domains wherein the net magnetization is aligned with the field, that domain starts growing in size, and those domains wherein the net magnetization is not aligned with the field, that starts getting shrunken over there, and as a consequence we find that the number of domains start decreasing. Some domains grow, some domains shrink. The magnetization which I generate by putting a paramagnetic material into the magnetic field, that happens to be up to 1 billion times more than what you observed in case of paramagnetic materials. Now, in case of ferromagnetic materials, we find that the magnetization which comes into play in the presence of magnetic field, that happens to be much larger, maybe to the extent of about 1 billion times more than what is observed for paramagnetic materials. That means, this effect is very strong, significant there. And if I continue increasing the field, that is in strong fields, what we find is the domains which are not aligned with the magnetic field, they become very small, and primarily those domains wherein the magnetic moments are that net magnetization is aligned with the field, they only sustain there, and we find that that is the effect which comes into play. Now, at this stage something very significant happens, that is, if I remove the magnetic field, the sample retains the net magnetization in the direction of original field. This is very different from what we observed in the earlier two cases of diamagnetism and paramagnetism. In both the cases, we found that the moment you remove the magnetic field, the effect is lost. But in case of ferromagnetism, we find that this effect is sustained. That is a basic difference between diamagnetic, paramagnetic and ferromagnetic materials there. Further, if I increase the temperature now, because at normal temperature the magnetization which is achieved by putting the material into magnetic field, that stays there, and the thermal agitation is there to disrupt that, but that is not significant enough to break that kind of an alignment, and the magnetization stays there. But if I keep on increasing temperature, a temperature might come, that is critical temperature comes, which is called as a Curie temperature, at which the magnetization which was staying back is lost and the material becomes paramagnetic in nature. So, that is typical behavior of ferromagnetic materials there. So, ferromagnetics are very different from what we had talked about, the diamagnetic and paramagnetic materials there. Let us move further and look at yet another kind of magnetic behavior, what is called as antiferromagnetism. Antiferromagnetism basically is a very different kind of phenomenon. What you find is that in some materials, they show a very different kind of behavior, wherein the coupling of magnetic moments does take place. Like in case of ferromagnetism, the neighboring magnetic moments were coupling, they were getting aligned in domains. Here also the coupling takes place, but what happens is the alignment of spin magnetic moments is in the opposite directions, anti. In the previous case of ferromagnetism, when the neighboring spins or neighboring magnetic moments were interacting, they were aligning in one direction and there was net magnetization in that direction. But in case of that is why it is called as antiferromagnetism. In this case, the neighboring spin moments align, but they align in the opposite direction. One is oriented upwards, other is oriented downwards there. As a consequence, the net macroscopic magnetic moment for the material is 0, because if they are aligning together, there is a net magnetization. If they are aligning in the opposite direction, the net magnetization will be 0 there. This phenomenon is called as antiferromagnetism. Let us look at this picture here. What you find is that we have our bulk matter here, shown by that white spheres over there, and what you find is that the magnetic moments on each one of these constituent species over there, so they are aligned. In one case, they are aligned opposite to each other. That means the two neighbors will not have same kind of an alignment. As a consequence, sum total of all that put together gives me a 0 net magnetization there. And this kind of behavior is observed when a paramagnetic material is cooled. When you cool it down to a certain temperature called as Niels temperature, and then thereafter there is a sharp decrease in the magnetic susceptibility and the so called paramagnetism is lost over there. So, that is another kind of a behavior we come across there. Let us look at one more kind of magnetism or magnetic behavior called as ferrimagnetism. This is a very tricky kind of a behavior. It is somewhere in between the ferromagnetic materials and antiferromagnetism. That means ferromagnetism and antiferromagnetism. In ferromagnetism, the neighboring things are aligned together and there is a net magnetization there. Antiferromagnetism, they are aligned opposite way, then there is no net magnetization there. And in case of ferrimagnetism, which is in between the two, we find that there is an alignment, that is like antiferromagnetic material, the phenomenon is also based on coupling of the magnetic materials, and there is an alignment there, but alignment is not complete. That means there is an alignment in the opposite direction, but they are not of equal magnitude. As a consequence, the material does exhibit some kind of a net magnetization like ferromagnets. So, it shows magnetism like ferromagnets, it shows a kind of opposite alignment like antiferromagnetic material. So, that is how it is in between the two kind of behaviors there. Let us look at this picture here. So, what you find is the constituent species here. So, we find that this is a magnetization here, this is a magnetization in this direction there. So, we find that the two are opposite, but they are not equal. That means these two magnetizations are not going to cancel each other. So would these two, so would these two. That means there will be the sum total of it will be such that there will be a net magnetization as in case of ferromagnetic materials, but at the same time ferrimagnetism comes as a consequence of the neighboring magnetic moments to be aligned in the opposite sense to each other. I think we have talked about all the typical possible magnetic behaviors of the matter. Now, let us sum up what we have done today. What basically we have done today is we started by reviewing the contents of previous sessions, and then thereafter we described the principle of measurement of dipole moment, where we used the Debye equation and things like that. Having done that, we moved on to explaining the origin of magnetic properties of the materials at atomic level, wherein we talked about the orbital motion of electron on the spin of nuclear, that is the electron spin and things like that. And then thereafter we discussed different types of bulk magnetic properties like diamagnetism, paramagnetism, ferromagnetism, ferrimagnetism and antiferromagnetism and things like that. With this we come to the conclusion of this series, wherein we try to talk about different kind of physical properties and correlated that with the structure of the materials there. Thank you.